Alright, hello guys, hope all of you are doing well. So in the present situation we are locked down in our respective in our homes. So it is the best time I think to utilize the time and study some new physics or known physics, you can say, obviously. Yeah. So today's topic will help you not only in your interview but also in your upcoming NET exam. This is a very important topic. I guess you already know from the thumbnail what I will be going to discuss. So without wasting any time, let's just begin the video. So I am Joyanto, as you all know, those who are following me. So today I'll be going to discuss Raman spectroscopy, a very powerful technique to get information about the heterostructure or to know the unknown molecule, to identify the molecule. It has many more applications in the industrial part and in the research. So those who are new to my channel, please consider subscribing if you want more this kind of topic in future. So without wasting any time, let's just begin the video. Well, so in this video, Raman spectroscopy will get in the principle and the basics of this technique. This is a really wonderful technique. We should know about this. This will help us in clearing some interviews or whatever the concept you have about Raman spectroscopy. It will also enhance. So talking about the slides, I will be discussing here some introduction, history, depending on the Raman history, whatever the history, how it is been developed, some basic principle, and the main important part, classical and the quantum theory of the Raman spectroscopy or Raman scattering, you can say. So some instrumentation part, and finally what are the application of this Raman spectroscopy, we'll also discuss in detail. So from the introduction, Raman spectroscopy is nothing but it is a spectroscopic technique which named after the Indian physicist C.V. Raman. So typically this is used to determine vibrational modes of molecule, although rotational and other low frequency modes of the systems also be observed. And it is known that Raman spectroscopy is the fingerprint of that molecule. That means every human being or every species, especially human beings, we have our different fingerprints associated with us, right? So every molecule or substance, it has also particular fingerprint or particular special property in it, and Raman spectroscopy that kind of tool. It can extract the fingerprint of that molecule and we can identify what is the molecule from this spectroscopy technique. So this is about quite a brief introduction. Well, how the history developed, let us look at the time lapse. So starting from 1923, inelastic light scattering is predicted by S. Meckel, and 1928, so Landsberg and Mandelstam see unexpected frequency shift in the scattering from quartz crystal, and in 1928 C.V. Raman, K.S. Krishnan see feeble fluorescence from neat solvents. Okay, and so in 1930, so finally the Nobel Prize came in physics for the Raman spectroscopy to C.V. Raman, a great scientist. So 1961, 1977 and 1997, so all these phenomena happen. So invention of laser makes Raman's experiment reasonably good, and today's Raman experiment, Raman spectroscope are very powerful to probe into the heterostructure and to identify the molecule to get the Raman shift. So it has many more applications, and over the time it has been also developed to its best so that we can get the best performance of it. So basic principle, or you can say, so briefly, what happens when light falls on a substance, right? So when light falls on a sample, many phenomena happen, like here you can see. So especially here you can see some reflection, it can happen, transmission obviously it can happen. It may absorb the incoming light and it can also scatter the incoming light. So if it passes through a transparent substance, a small amount of radiation energy is scattered, and if monochromatic radiation is used, it will be elastically scattered, and this is known as the Rayleigh scattering. So we are mainly focusing on the scattering part to discuss the Raman scattering or Raman spectroscopic technique. So two type of scattering mainly happen. One is elastic, that is in that part the incident light is coming and it will be scattered without change in energy or change in frequency, you can say. So that is the Rayleigh scattering we know. And also some higher and lower frequencies will be scattered inelastically, known as the Raman scattering. So the molecule will gain energy from the incident upcoming light wave, and its frequency will be shifted to higher or lower side. That will we are going to discuss in detail in later. So talking about the quantum theory part, so as you can see, wait just a minute. Okay, so in the quantum theory part, you can see here that incident energy of h nu 0, so or h nu e, I think, so it is not clear though. So h nu, let us assume that it is h nu. So h nu energy of light is falling on a molecule, and the molecules have some vibrational level in it. So it has ground state, it has fast excited vibrational state, second, third, and so on. So the molecule will be excited from the ground state, they will go to some virtual energy level, and they will also decay to the ground state itself. So whatever the energy is coming, that will also be emitted in the form of photon. So there is no change in frequency or no change in energy for the incoming light. So this scattering is called the Rayleigh scattering, in which basically there is no change in energy. Alright, so here I am talking, it is a virtual energy level. So virtual energy level is nothing but, so the molecule can be excited to some higher energy level than the ground state, to some arbitrary energy level. That is why we are calling it a virtual energy level. So it is the concept of it. So now this Raman effect can be understood very well in the light of quantum theory. So I have already told what is Rayleigh scattering. Now what happens in Raman scattering? Now if the energy is exchanged by the photon and the molecule may be advanced to a higher energy state or level or virtual state, and there might be different outcomes. Like if the molecule relaxes to a vibrational energy level that is different than of its beginning state, producing photon of different energy, and the relax to a final energy state that is lower than that of the initial excited state, this scattering is called the anti-Stokes line. So here is the anti-Stokes line. So if the molecule which are getting excited from the first vibrational energy state, and they are going to a virtual energy level and then coming back to the ground state. So it starts from the fast vibrational energy level and decaying to the ground state. So in this case, as you can see, the energy that will be coming out, that is higher than the incident energy, or you can say there is a shift in frequency to the higher frequency side. So the frequency which is greater than the incident light is known as the anti-Stokes scattering. So this is due to anti-Stokes scattering. Now what is Stokes scattering? So here in this figure you can see Stokes scattering is nothing but if the molecules are getting excited from the ground state. So if the molecules which are excited from the ground state and going to some virtual energy level here, and then coming back to the fast vibrational excited state. So as you can see in this case, the energy gap is less than the anti-Stokes scattering, and it is also less than the main energy of the photon that is incident on the molecule. So in this case the energy will be less, so the frequency will be less after the scattering, and this is known as Stokes scattering. So this is a little bit about quantum theory. Now in this figure, neglect this part, we have already discussed these things. So consider on this figure. So this is a typical plot, intensity versus the frequency. So nu x is the external frequency of the incident light that is falling on the molecule, right? So if you notice carefully, you notice that the intensity of the Stokes line is much greater than the intensity of the anti-Stokes line. So you can say, why is it so, right? So this can be easily explained by the maximal Boltzmann distribution function. So right, at normal temperature, room temperature, the molecules will be mostly in the ground state. So they mostly be likely to stay in the ground state, right? So go to the previous figure. So mostly the number of molecules are staying in the ground state is much more higher than they are in the excited state. So in case of Stokes scattering, so it is happening from the ground state. So there is many more molecules which will be excited to the virtual energy level and then come back to the fast vibrational state. But in the case of anti-Stokes scattering, the molecules are getting excited from a fast excited vibrational state. So Maxwell-Boltzmann distribution says like n equal to n to the power minus ei by kBd, ei some particular energy level. So at particular energy level, for the excited state, the number of molecules will be less than the ground state. So here less number of molecules are going to the vibrational energy level and then coming back to the ground state. So that is why in this case intensity will be less. Why intensity is less? So intensity basically what the detectors see how much the photon is coming after scattering. Okay, if there is more photon is coming, then the intensity will be high. If there is less photon is coming, then the intensity will be less. So in the first case, as many particles are in the ground state, they are getting excited, so more and more photon will be emitted in Stokes scattering. And in anti-Stokes scattering, less number of photon will be emitted because of the population in the fast vibration state was less than that of the ground state. So that is why in the second case number of photon is less. So that is why here intensity is also less. Okay, so here a Raman shift you can also calculate. So shift from nu x to nu x minus nu v, or here. So this shift is equal for Stokes and anti-Stokes line. Okay, now talking about the classical theory. So before going into the classical theory or understanding the classical theory, first we need to know what is the induced dipole moment, how dipole moment can be induced in a molecule in the effect of external electric field. So like if light is falling, it has an associated electric field, right? Now if the electric field is steady, so in a molecule there is positive core nucleus and the electrons are rotating, so electrons cloud are also there, right? So if static electric field falls on a molecule, then the electron cloud will shift to the positive part of the electric field and the positive and nucleus will slightly move to the negative part of the electric field. So there will be a clear charge separation, or there will be a separation between the center of positive charges and negative charges. So that will induce a dipole moment in the molecule. This is the case of static electric field, right? Okay, now what happens if the frequency is time dependent? So it has a particular frequency of electric field, has a particular frequency, but it is time dependent. So you can say like AC voltage or AC current. Okay, so the electric field is oscillating with respect to time. So now here if the electric field is oscillating here, there is a dipole moment which are created that will also oscillate like this. So there will be dipolar oscillation induced in the molecule. So here I am showing some diatomic molecule. So here diatomic molecule, their bond, their separation between the positive and the negative charges, they will oscillate like this, or in any fashion they can also oscillate. Okay, so as we know from the theory of electromagnetics that a oscillatory dipole or dipole which are undergoing oscillation, it will emit radiation, right? So this oscillation of the dipole will emit radiation, and we can show by calculation that the radiation emitted will be of the same frequency as the electric field, and there will be higher frequency and lower frequency than the frequency. Okay, now before going to the classical theory, one concept we should know: what is the polarizability of a molecule? So polarizability of a property of an individual molecule, it changes for different molecules. So it has a characteristic property, you can say, of that particular molecule. So what is polarizability? So polarizability we define is as dipole moment induced per unit electric field. So how a molecule can easily be dipolarized, or how easily we can create dipole moment in the molecule with the application of the electric field, that defines the polarizability. So if it is more easy to polarize the molecule, then we can say the polarizability is high for that particular molecule. So like here if we consider a dipolar molecule, CO2, as you can see here. So now if the in the application of the external electric field, now this C and O bond will oscillate like this, or this can also oscillate in this fashion. So or it can also create rotation. So now if this O are moving like this, vibrating like this, then there will be a change in the polarizability. So like if the bond strength is increased from C to O, this O has been initially this point and now it is at this point. So then it will be more easy to polarize this molecule when it is stretched. So that means there is a change in the polarizability of the molecule. Now here in this case, if this C and O atom are moving like this, then there will be no change in the polarizability. So what change in the polarizability that is incorporated by this O molecule, that will be subtracted by this O molecule. So in this case, though there is change in dipole moment, but there is no change in polarizability. So likewise this O can move in this fashion and this O can move in this fashion, or randomly they can move in any ways. So in all those cases where there is a asymmetric vibration in the dipole molecule, then there will be no change in the polarizability. So if there is no change in the polarizability, then we call it as Raman inactive. So a molecule will be called Raman active if only if there is change in the polarizability of the molecule. So here there is change in polarizability, so it is Raman active, but here is no change in the polarizability of the molecule, so it is called the Raman inactive IR. Okay, so this is a little concept about polarizability. Now we will understand how the classical theory can explain the Raman effect very easily. So I have some handwritten notes here. So let's say there is a electric field experienced by each molecule given by this equation. Nu is the frequency of that electric field. So now if you go to the classical theory, now this electric field will induce dipole moment in that molecule. So we define dipole moment like this way. So so here dipole moment, so mu I have defined alpha into E. Alpha is the polarizability of the molecule and E is the electric field. The equation is like this. So mu is the induced dipole moment, you remember. So now dipole moment has been induced in the molecule. Now what will happen? So now we know oscillating dipole emits radiation of its own and oscillation frequency. So I have already discussed it previously. So it will give rise to Rayleigh scattering if the frequency, if the dipolar are oscillating in the same frequency as the electric field. Now what happens? Other than oscillating with same frequency, let me refer to Banwell, that will be more easy and more detailed. Okay, now here. So this book is from Banwell, this write-up from Banwell. So like so if in addition the molecule undergoes some internal motion, such as they can vibrate or rotate, which changes the polarizability periodically, then the oscillating dipole have superimposed upon it vibrational rotational oscillation. So apart from the frequency of oscillation that is set by the electric field, it will also induce vibrational frequency, new vibration, which changes the polarizability like in this equation. Now what is beta? So beta represents the change in polarizability. So rate of change of polarizability I have defined here, d alpha by del q. So this is the change in polarizability. So now if you put this alpha equal to this equation in the previous equation here, mu equal to alpha into E, then you can easily get this equation, and then you can expand this equation, this sin A sin B formula you can easily get. Then you can see here, so in the first part here, as you can see, so here, so you can see there is alpha 0 epsilon E0 sin 2 pi nu t. So there is main frequency as that of the electric field, and apart from there are also frequencies which is lower and higher than the frequency of the electric field. So that is how the frequency is set in the dipolar oscillation apart from the original frequency of the electric. So that dipolar oscillation will emit radiation of these three frequencies. So the fundamental frequency I have called it the Rayleigh scattering, I have already told. So lower frequency is due to the Stokes scattering, and the higher frequency is due to the anti-Stokes scattering. So this is the theory classical point of view to discuss the Raman effect. So carefully, if you note, go through this equation. So in this equation I have defined beta is the rate of change of polarizability. So let's say if there is no change in the polarizability of the molecule, then beta is 0, right? So this two part will vanish from the induced dipole moment. So here I have said beta equal to 0, then dipole oscillates only at the frequency of the incident radiation. So only this part will remain. Okay. So this part will remain. So that is why beta needs to be non-zero for it is to be called a Raman active molecule. Okay. So I have discussed the detailed theory of classical theory related to Raman effect and the quantum theory. So to sum up, what should be the conditions for Raman spectroscopy? So as I told, Raman spectra occurs as a result of oscillation of a dipole moment induced in a molecule by the oscillating electric field of the incident wave. So as the induced dipole moment is directly proportional to the polarizability of the molecules must possess anisotropic polarizability, which should change molecular rotation or vibration for vibration and rotational Raman spectra. And anisotropic polarizability depends upon the orientation of the molecules. Obviously, how the molecules are oriented, that polarizability should depend upon that configuration. And in the presence of an electric field, the electron cloud of an atom or molecule is distorted and polarized, that I have already told. Okay, now let's get back to the instrumentation part. So in the instrumentation, before going to extract the Raman spectra, so Raman spectroscopic graph from that molecule, we must be aware at what wavelength the molecule are absorbing the incident photon, and what is the particular wavelength or particular wavelength broadening for that the molecule also show photoluminescence. So some molecules show photoluminescence, so we should avoid that particular wavelength. Why? If say I have induced a particular wavelength in that range, the molecule shows photoluminescence, then the molecule will emit photon in that wavelength. So then I will not be able to get the actual Raman scattering from that particular frequency. So initially we have to decide what wavelength of laser we should use that will fall on the sample. Okay, so let's say I have decided a particular wavelength, say some 480 nanometer. Then the configuration of the Raman spectroscopic setup is looking like this. Some laser is there, some ND filter, beam splitter, and this one is some dichroic sorry. So here is the dichroic mirror should be this. So some objective lens, and finally the sample is here. So laser will be emitting a light that will fall on the sample, and the part of the light will be beam splitted and will go to the spectroscopic unit, and then it will go to the CCD detector, and the final graph will be produced in the digital form in your PC. So you can go through all this part. I have made the handout notes here. You can know what type of laser we are use, argon ion plus and HENE laser we are use. This two type of wavelength we mainly use here. So ND filter is here. So you can pause the video and you can copy all this information, or you can go through online, find some literature there. Okay, so I am not discussing in detail, it will elongate the video. So for the instrumentation part, you just go through all this. Okay, so this is a particular Raman spectra. So intensity versus Raman shift is there. So many more Raman peak are there. From this we can identify the molecule. So this is a Raman spectra for TiO2 sample, and only here anatase phase are determined. So forget about that. So this is for data analysis. Here the main motive was to share with you the basic concept of the Raman effect. Okay, some analysis parts are there, conclusion, and let's go to the application of the Raman spectroscopy. So Raman spectroscopy is used in the industry for a variety of applications. So initially I told that it is the fingerprint of the molecule. So to identify an unknown molecule, Raman spectroscopy is one of a finest tool we have. Also we can analyze crystallization process, polymorphism identification, polymerization reaction, and synthesis reaction, etc. And this fingerprint part I'm discussing again and again. So here are some reference you can go through. So that's for it today. So thank you. Okay guys, this is little bit concept about Raman spectroscopy. I hope you have some gather idea from the video. So if you found this video really informative, then make sure you subscribe to my channel, and also most importantly hit that notification bell icon so that every time I upload a new video you will be notified as soon as early possible. So in the next upcoming videos I will come up with a problem related to Raman effect that will also be helpful for your NET exam. So basically I am planning to start a molecular spectroscopy course, so I am starting with the Raman effect now. Okay guys, thanks for watching till the end. Thank you once again all of you. So I will be meeting you soon when I upload new videos. Okay, so that's for it today.